Please,
So,
Raffaella.
Start this last session of the meeting to Nonlinear Days in Urbino 2021. The first speaker of this afternoon is Maria del Mar González Nogueras from Universidad Autónoma de Madrid. She will speak about non-local ODE in conformal geometry. Please, Maria.
Okay, thank you, Rafaela, for the introduction, and thank you to the organizers for the invitation. It's a pity that it's not a present meeting, but it's still nice to be here online. And also because you've managed to put together a lot of mathematicians in linear analysis, but they come from a little bit different communities. So it has been very nice to learn all these new things. Okay, so I think this is a very good idea. So like take people from a little different areas. Okay, so I'm going to tell you a problem that I have been interested in the past few years, and it's to do non-local ODE. And they come from, my ideas originally come from conformal geometry, but I will talk very little about geometry, and I will focus mostly on the analysis part. So let me tell you the motivation. I'm going to look for radially symmetric solutions of, okay, let's just look at the local case, minus Laplace of u equals u to the p, and I'm going to look for solutions that tend to infinity as r goes to 0. I mean, I'm looking for singular solutions that are singular at the origin. Okay. It is well known that this u has a very particular asymptotic behavior at the origin, so it is very natural, and I mean, this is just very classical, to change variables to this exponential. They are calling them Fowler coordinates, and then to change from u to v. So now u picks the singularity, and v is bounded. Now this t now is it belongs to the real line r, and I forgot to say that. Even though this equation is going to be valid for several values of p, just because it's easier to write, I'm going to concentrate on the critical p n plus 2 over n minus 2. So anyway, when you do all these changes of variables, what you obtain is just an ODE, a usual ODE in R that you can do by analyze by phase portrait. Then, okay, when you change coordinates from r to t and from u to v, and keep this notation because I'm going to be playing with it for the rest of the talk. So u has the singularity, v is bounded. So what you obtain is this ODE here, and you see that all the r factors disappeared, and so it is an autonomous equation. So now you can do phase plane analysis, plot v against v prime, Vt, and it's well known that this equation has an homoclinic solution and then a sequence of a family of periodic solutions. Okay, but something I would like to say and advance now is that this part here on the left-hand side of the equation is P1, and P1 is the conformal Laplacian on the cylinder. So basically what you are doing with these changes is to go from R to the cylinder, and this is going to be the underlying idea that is going to, well, the key idea for this talk. Like when you go from Rn to the cylinder, then your equation becomes autonomous, and then you can do some kind of, well, you cannot do a portrait. Oh, what's that? Oh, well, never mind. Anyway, so now let's move to the non-local case. Okay, so just to fix ideas, I'm going to take n greater than 2 gamma and gamma between 0 and 1, and I'm going to be looking at the fractional Laplacian of power gamma. Now, the problem is that, again, I'm going to look for radially symmetric solutions of the semi-linear equation minus Laplace to the gamma u equals u to the p. For simplicity, I'm going to take p to be the critical power, that in this case is n plus 2 gamma over n minus 2 gamma. And again, I'm going to look for solutions that have an isolated singularity at the origin. By this, I mean that they blow up to infinity as you approach the origin. Again, you take the change of variables r equals e to the minus t, and you change from u to v so that now v is a bounded function. Now recall that my new variable for the ODE is going to be t belongs to r. And again, when you make these changes, then your original equation is equivalent to the following one. Okay, it's not so direct to write the Laplacian in polar coordinates, but if you do some work and you do all these changes, what you obtain is an equation that mimics the equation I obtained for the Laplacian, in which you have p gamma v equals v to the p. And here you don't say much because I didn't tell you who p gamma is, but in some sense, this equation is also autonomous. So somehow now you try to think, okay, if it's true for P1, then it's going to be true for P gamma. Well, maybe, sometimes. But now you don't have a formula for P gamma, you cannot do phase portrait, you have a non-local ODE. So you don't even have theorems of existence or uniqueness, continuous dependence of initial data, etc. So basically you have to start your ODE theory from scratch. Just proving even existence is not trivial. Okay, so now, for instance, for this particular equation in the critical exponent, we have a proposition joined with De la Torre, Del Pino, and Junchen Wei, that we prove that we still have the same pictures that in the local case you have an homoclinic and then a bunch of periodic solutions, but of course you don't have you cannot do phase plane analysis, and the proof is variational. I'll give you some more ideas later about this proof, but I don't want to. This is an older result. Let me tell you who this P gamma is. So this P gamma is the conformal fractional Laplacian on the cylinder. So as I said, when you change variables from r to t and u to v, you are passing to the cylinder. How do you see this? So geometrically, let me consider the Euclidean metric dx squared and divide by a singular factor r squared. So actually this new metric is conformal to the Euclidean one. Let me write the Euclidean metric in polar coordinates, so it's d r squared plus r squared over d theta squared. Make the change of variables r equals c to the minus t, and you obtain that this conformal metric is d t squared plus d theta squared. So it is the cylindrical metric because t is the r variable, and then you multiply it by a sphere of 1 dimension less. So this is exactly the cylindrical metric. So somehow when you make this change of variables, I mean, this is what it justifies what I told you, that you are passing to the cylinder. So in some sense, since the v function was bounded, you are moving the singularity from the function to the metric. Now this metric is singular at the origin, but the solution of the ODE is bounded. And this makes things much easier. Okay, so now this P gamma operator, who is this guy? When you multiply and inside out and you take into account these r factors, you see that this P gamma is just an intertwining from the fractional Laplacian. And this the intertwining rule is something that Nicola mentioned yesterday in his talk. So this is the same intertwining rule in conformal geometry. But somehow when you make this rule, this P gamma is much better behaved, especially when you talk about polar coordinates. Okay, so who is this P gamma? So the first definition that we gave, or construction that we gave of this operator was via extension. And if you remember the construction of Caffarelli Silvestre for the usual fractional Laplacian, for this operator, it's actually similar. You have to do it as a Dirichlet to Neumann operator for a suitable Caffarelli Silvestre extension, and the geometric setting you have to extend to anti-de Sitter space. So now just a punchline for to tell non-mathematicians. Ideas anti-de Sitter space is the simplest example of a black hole. So this type of metrics were developed by Penrose. Okay, so if you do the Dirichlet to Neumann operator for this Caffarelli Silvestre extension, then you get a conformal fractional Laplacian on the cylinder. But let me tell you a little bit more on its properties. So consider the spherical harmonic decomposition of the unity sphere Sn-1. So then you know that you can define some em, they are the eigenfunctions of the Laplacian, mu m the eigenvalues. So, and these em are a complete basis for the spherical harmonics are a complete basis on the sphere. So essentially any function on the cylinder R cross Sn-1 can be decomposed, can be expanded into this eigenfunction basis. So instead of writing the operator applied to U, let me just write the projection to each UM. Okay. So now the theorem, this was the first result in my student's thesis like a few years ago, is that P gamma diagonalizes under spherical harmonic decomposition. So basically it's enough to calculate the different projections applied to each UM. And moreover, you can, if you do Fourier transform in the variable t, because UM depends on the variable t, let me call the Fourier variable xi. Okay, let me take the Fourier transform of this operator and see what is the symbol. So you see that the Fourier transform of P gamma UM gives you UM hat with a symbol theta gamma. And now the formula for this theta gamma is written down here. But don't worry, it looks awful because it has some complex gamma functions, but it looks ugly, but it's actually not too bad because it has good properties that I will tell you. But anyway, every time you have to work with these things, you will have a lot of special functions running around. Now, for the rest of my talk, since I'm only looking at radial solutions, let me look at the projection m equals to 0, and I drop the superindex m. And let me concentrate on m equals to 0 on radially symmetric solutions. So the properties that you see down here, this can be extended as a meromorphic function in the complex plane, and this is going to be quite important. And then if you look at the asymptotic behavior at infinity of this symbol, actually you see that you recover the symbol of the fractional Laplacian. So this operator, it looks awful. Well, no, it's not that awful, but behaves as the usual fractional Laplacian in some sense. So you will see that how I'm going to use these properties later. Now, a more recent work that we are writing now is that we can reprove the formula for the symbol using Mellin transform without knowing any geometry. And this is joint work with Hardy-Chan, Marco Fontelos, and Junchen Wei. Now, define the Mellin transform as, okay, let me call it M of U. And okay, you can choose a parameter alpha. But the Mellin transform is just the integral of U against some R to some power. The main properties that this transform has, it is that for alpha equals -1, the Mellin transform is just the Fourier transform coupled with this exponential change, R equals e to the minus t. So Mellin and Fourier are the same under a logarithmic change of variables. Now, for alpha is equals -1/2, it's an isometry in L2, so it's easy to go from the function to its Mellin transform when you talk about L2. And now, to prove a formula for the symbol, instead of looking at the Fourier symbol, you can look at the Mellin symbol. I mean, they are the same because under this exponential change. So basically, what I'm going to try to reprove the formula for the symbol, but not using Fourier, using Mellin. So basically, how do you prove this? Recall that P gamma was an intertwining rule from the fractional Laplacian. So just put the R factors in and out, and it's the same. And now calculate the Mellin transform of this. So the Mellin transform of this, okay, you have the R factor, and you have to calculate what is written in yellow here, the Mellin transform of the fractional Laplacian. I don't know what it is, but I know that the fractional Laplacian under usual Rn, so let me put this is the Rn Fourier transform. It has the principal symbol k to the 2 gamma. So stick that in, put Fourier in, Fourier out, put all the R factors, and calculate. So when you calculate this, you hope to recover that symbol here. And this is what we did, and that's the proof. The rest is just technicalities. Now, two things that we use, that the Fourier transform in Rn can be written in terms of, okay, some Bessel function J, etc. So it's actually the Hankel transform, and then you see that you need to integrate a bunch of Bessel function times powers of R, and then when you put all this in those integrals, you see that you end up obtaining a lot of gamma functions. And this is the proof of the symbol. And you see it has no geometry, just a simple analysis. Okay, another characterization of this gamma operator was given in the same paper I mentioned before, in the La Torre del Pino González way, where I gave an integral formula for this P gamma. This P gamma can be written as a convolution with a singular kernel K of V. Okay, then there is plus a zeroth order term, where the important thing is that this K operator, it has, as t goes to 0, it has the same singularity as the one-dimensional fractional Laplacian. So actually this is what expected, because I'm looking at the radial projection and the real solutions. But at infinity, it has exponential decay, so it has a much better behavior than the fractional Laplacian, and this is something that we use quite crucially in our papers. And this one, if you look at probability, this one corresponds to tempered stable Levy process. So in some sense, even though the formula for this P gamma is more ugly, it's uglier, its behavior is its analytical behavior is much better due to this exponential decay. Okay, so now let me start moving to the heart of this talk and say, okay, how do I use this P gamma to solve a non-local ODE? So now most of the arguments I'm going to tell you now are in this in the Duke paper. It's okay, we're 6 authors, but the paper is like 115 pages. So joined with Wei Yao, Hardy Chan, Azara de la Torres, Marco Fontelos, and Junchen Wei. Now we also have a survey, so maybe it's much easier. It's easier to read the survey than trying to read the original paper, because we did some gluing for for fractional Laplacian equations, etc. But let's not worry about it. Okay, so now the question I'm interested in is the following one. So it's the fractional Laplacian of U. Let's stick to the linear case, minus kappa. Kappa is a constant divided by R to the 2 gamma U equals F. So I'm interested in the invertibility properties of this equation. Now, you see that this kappa of R to the 2 gamma, this potential term is a Hardy potential, but it's critical, because you see the homogeneity of this R to the 2 gamma is the same one as the homogeneity or the order of the fractional Laplacian, so they are competing with each other. But now, the nice thing is that when you change from Rn to the cylinder, then your new equation becomes written in terms of this P gamma, is P gamma phi minus kappa phi equals h, where phi is just a function on T on the cylinder. So by making this change happen as what I explained before, the equation, the R factors disappear and the equation becomes autonomous. Now, so how do you solve this equation? Let's look first at the invertibility properties. So, okay, we know the Fourier symbol. So let me take the Fourier transform in the T variable, and what you get, okay, P gamma, the symbol is theta gamma. So you get an equation in Fourier variables for phi hat equals, okay, the right-hand side. Now, I want to invert this, so I isolate phi hat. Okay, is this legal to make this inversion? Okay, I'll tell you something more about it later. But let me take Fourier transform back to write phi. So phi is the inverse Fourier transform of of whatever of this expression, and now this is written in terms of h hat. So let me write what h hat is. It's just the Fourier transform of h. So I write it in terms of h just by write the definition of the Fourier transform, and now collect the yellow terms that depend on xi. And collect the yellow terms and put them into some g function. Now what you realize is that you have recovered the formula for your solution phi of t as the integral of g of t minus t tilde h of t tilde dt tilde. This means that I have recovered the solution of my equation as the convolution of my right-hand side with a Green's function. So actually, this is just the usual Green's formula, or if you want, it's like doing variation of constants to obtain a formula for the solution of a constant coefficient ODE. Well, more or less. But philosophically, this is the idea. So just do variation of constants. Okay, now, but is this legal, this formal calculation? And the thing, yes, it is legal, except that you are dividing by this term, and this denominator will have zeros, and will have zeros in the complex plane. So the hard part of this paper was to figure out where those two zeros are. So the zeros of this complex function can be characterized in the complex plane, and they are an infinite number, but at infinity they have the asymptotic behavior is controlled, so you can do complex integration and apply the residue theorem to find this formula for this g, so there is no problem in that. And then you have just a finite number of poles here, but they don't bother too much. But when you put them all together, you get an infinite number of indicial roots. Let me call it sigma j. Okay, maybe some sinus and cosinus, but let's not worry about the sinus and cosinus part, just to keep for simplicity. And when you put this, when you calculate a formula for this g, when you integrate in the z variable, then you get a formula for your Green's function that it's an infinite sum of this exponentials at the initial roots. Okay, so let me compare with what you know about the method of variation of constants for second order ODEs. For second order ODEs, the first thing you do is to solve the homogeneous problem, and you know that for this homogeneous problem, the solution is composed by two exponentials, and the exponents are precisely the initial roots of the equation. So in some sense, if you do this argument for a second order ODE, you are going to get that your g is the sum of two exponentials, because you only have two initial roots. When you do a non-local equation, or like for this fractional Laplacian, you get an infinite number of initial roots, but you get the same structure. So let me tell you why is this interesting, but keep this in mind that I'm trying to see how much of the second order case I can do for this case, just take into account this infinite number of initial roots. So I guess the most interesting consequence is that recall that I wrote phi as the convolution with a Green's function of the right-hand side, substitute the definition of the Green's function up here, and when you put it all together, okay, just formally interchange integral and summation, etc. Call all the yellow part to be phi j, and actually just look at the end. What you have obtained is just your solution of the ODE. It's phi of t. It's just the sum of an infinite number of some phi j with some constants. Let's not worry too much about it. But important thing is that phi j is a solution of a second order ODE. And actually this was surprising, because in summary, what I have told you is that you can rewrite an non-local ODE as an infinite system of coupled second order ODEs, and the coupling comes because of the right-hand side here. And this is the punchline. So non-local ODEs, okay, they you have to do all the theorems from scratch, but you can rewrite in terms of infinite number of second order ODEs. So from here you can do Wronskians, Hamiltonian arguments, etc. Just take into account that you have an infinite number of initial roots, so that sum is infinite. Okay, I mean, of course, I'm oversimplifying, but you have to take care of convergence, etc. But you can do it. And this is the punchline of my whole talk. Now, let me just now mention that I told you what happens in the constant coefficient case when you have a kappa in your Hardy potential. This theorem, you can use these methods to handle when you have a potential term here, this V of R. And this would be like the non-constant coefficient case, and etc., etc. But I don't have much time to talk about that. And this guy is important because it is this is the linearization. It is essentially the linearization of the ODE that I wrote at the beginning. Okay, so now in the time that I have left, let me tell you about some applications of this non-local ODE theory. And the first thing is that we developed some fractional version of the Caffarelli-Nirenberg inequality. This is a joint work with Weiwei and Zabra de la Torre. So we did some results on symmetry breaking, on degeneracy and uniqueness. I will go over these results in a moment, but let me tell you what the Caffarelli-Nirenberg inequality is. Now, I have written here the inequality in the local case, gamma equals 1. So the Caffarelli-Nirenberg relates the Dirichlet energy of U to some LP norm here for this P critical, and with some weights depending on two coefficients, alpha and beta. Now, in the local case, we wanted to do the same. We wanted to write the fractional energy that is actually written here, the energy for the fractional Laplacian, but we proposed to add the weights here. And sorry, I think this is not an alpha, this is a beta. So this is our inequality, and let me tell you what we know about it. So, for this inequality, we know that the best when the best constant is achieved, and if it's not achieved, we know that who is the enemy. It's just an R to some power function, so there is not it's not difficult. It solutions, minimizers, or optimal solutions for this inequality satisfy the modified inversion symmetry, and it's written in. I mean, it's just this modified inversion symmetry. It's a simple moving plane argument for a non-local equation using the kernel formulations. Let me get to the most interesting results. Now, optimizers, you know that in the local case there has been a lot of important works trying to understand when the optimizer is radially symmetric or when there is symmetry breaking, and maybe you have seen in the local case, maybe you have seen this picture where you plot the different values of alpha beta, and you have a yellow region of symmetry, a purple region of symmetry breaking, where your minimizer, the optimizer, is not radially symmetric, and in between you have a red curve that is called the Feli-Schneider curve, and that separates the region between symmetry and symmetry breaking. Okay, in the local case, you can do some the same picture, and actually there some of the proofs that in the local case also hold in the non-local case. And And again, you have a symmetry region and a symmetry breaking region. But here something is different from the local case, is that let me look at this -2 gamma. When alpha reaches -2 gamma, the Feli-Snyder curve, and we prove that there exists a little piece of this Feli-Snyder curve. I mean, we don't know what happens. We believe that it's the same thing. It will arrive to the origin. But the Feli-Snyder curve crosses the, let me put them this blue line. So in general, many of the results in the local case will hold for the non-local case, but this Feli-Snyder curve is different. Now the proof is not, I mean, it's the standard argument. You have to, if you want to have symmetry breaking, then you have, what you do is you perturb a minimizer in the direction of a negative first eigenvalue. And that decreases the energy and introduces some symmetry breaking. But here it was curious that we could, I mean, we had that a little bit different behavior in the local case. And Veronica, if this is something that I would like to talk to you, I mean, at some point, whenever this COVID lets us travel again. Okay. Now, what are the ideas for the proof of these results? The first thing is that we are going to rewrite the functional and its Euler-Lagrange equation from Rn to cylindrical coordinates, as I did, as I explained at the beginning of the talk. So when you rewrite the Euler-Lagrange equation, what you obtain is an equation for P gamma, a nonlinear of the same type that I told you at the beginning of our usual P gamma on the cylinder. So now, because we have too many techniques for this P gamma, then we can say many things about it. So that's the main idea. So for instance, we can prove non-degeneracy in the radial sector. So imagine that you have a radially symmetric minimizer, V bar, and let me linearize the operator around this minimizer here. So here L is the linearization. Now, if you take the equation that V satisfies, a note is that the derivative of this V bar belongs to the kernel of L. It's a solution of LW equals 0. Now, the non-degeneracy theorem is that the kernel of L is generated by this particular solution, and there is nothing else. So the proof, again, none of the type of arguments for this P gamma. And now we also have a theorem of uniqueness of minimizers up to translation in T. And the proof is a unique continuation argument as gamma tends to 1 that was developed by Frank Lenzman. So basically, if you have two solutions at gamma, then you do unique continuation, move on gamma, arrive up to gamma equals to 1. You will have two solutions, but in the local case, you know that the solution is unique, so you could reach a contradiction. So this is the classical argument of Frank and Lenzman, and we realized that it relies on spectral properties of the symbol, not on the formula of the fractional Laplacian, because our symbol of P gamma, it was this theta gamma that I wrote at the beginning, and I told you it had good properties. Then you can redo the Frank Lenzman proof. So actually, so as I told you, the symbol has an ugly formula, but it has much better properties. Okay, and now in the last 10 minutes, I will mention another application. And this is something that, I mean, this is newer work, like from last month, maybe, that again joined with Hardy Chang, Marco Fontelos, and Yunchen Wei, in which we developed a regularity theory for this equation in red here. And now, so it has a fractional Laplacian it has a potential term of Hardy type with a critical Hardy type for kappa constant, but then it also has a drift term. So I'm going to look at invertibility and regularity theory. Now this problem for radially symmetric solutions. I mean, I guess you can do for other solutions, but let me concentrate on the ODE case. Now, this problem comes from looking at type 2 singularities for the semi-linear heat equation, but we have to start from the linear theory because we didn't even have invertibility. So now, define this E gamma, it's going to be a weight that is the inverse Fourier transform of an in Fourier variables is an exponential. So if you are in the case gamma equals to 1, then your E gamma is the inverse Fourier transform of an exponential, it will give you an exponential. So this tells you that in the local case, your weight is going to be an exponential. In the non-local case, this is not exponential anymore, it's potential. But it plays the same role. So now for this equation, so what can you say about the regularity? You see that while the Hardy part and the fractional Laplacian have the same order of regularity, the drift is competing with the fractional Laplacian because the drift is order 1 and the fractional Laplacian is order between it can be anything between 0 and 2. So actually this is interesting when gamma is, I mean, you have for all range between 0 and 1, but if gamma is above 1/2, then the diffusion wins. So actually this is interesting when gamma is less than 1/2, so we don't know if the diffusion can compete with the drift. But still, our theorem is that under some Fredholm condition in terms of this weight that I defined there, I mean, of course, you need a Fredholm condition in order to guarantee uniqueness. Then we have that the regularity of a solution U is improved from the right-hand side by 2 gamma order. So this means that you recover the same regularity as a fractional diffusion, and the drift term is not bothering you. So what is the proof of this? So just to give you a rough idea, let me consider the case that you don't have a Hardy potential. Recall that the kappa was appearing here. Let me put kappa equals to 0. So if you have kappa equals to 0 and you take Fourier transform of the equation, just for notation, let me call to be rho the Fourier variable and to write the v as u hat. When you take Fourier transform of the equation, what you obtain is this simple ODE in v. You can integrate this formula. Let me just write a formula that is valid near infinity. So you have an explicit solution for this V of R. Okay, now just to get the regularity theory or in the space H gamma, or sorry, H alpha, H in H spaces, just work out with this formula, use Cauchy's, well, it's more complicated story, but you just estimate from this formula. So now keep this idea. If I want to have regularity for this equation, take Fourier transform and write an explicit formula for the solution and then estimate. Okay, so the same thing we did in the case when you have a Hardy potential that kappa is not 0. Let me take kappa less than the Hardy constant. This is actually the range that we need, because otherwise, if you go above the Hardy constant, you start seeing poles of those poles that I told you at the beginning, and let's not make our life complicated. Okay, so now recall that I told you that you could calculate the symbol of P gamma in terms of the so you could do Fourier transform or you could do Mellin transform. So let me use Mellin transform. Take your equation, the one in red, take Mellin transform here, calculate And what you get is this equation here. And you see that the symbol is coming up. So the drift is giving you this, this part. So you have the diffusion term, the potential term, and the drift term. But if you look at this, is that you have an equation that lives in the complex plane, lambda in the complex plane, that relates the values of V in two different complex lines. Okay, and these equations are classical. Okay, they are very old. They are very old. So now let me do just kappa equals to 0 for a moment, and then I will go back to the general kappa. If I make this change of variables, pass from V to W, and actually to guess those coefficients, those gamma functions, it took us like weeks, like a few weeks just matching coefficients. But if you insert this into the equation, you manage to kill the coefficients, and now you really got an equation that relates W over two complex lines, and you got rid of the coefficients. Now, this is actually very classical and is known as a Riemann-Hilbert problem. And then you can use your complex analysis to find a solution. So make a logarithmic change of variables in the complex plane. Those two parallel lines will converge both to a semi half line, but one will be like from above and the other one from below, and the log will have a jump. So now you can write in these variables, basically what tells you the jump from the upper part to the lower part is written in terms of a Cauchy integral. So you can write an explicit formula for this W in terms of H, and then once you have an explicit formula for your solution, just estimate. Okay, it's a little bit tricky to estimate this, but we found that it was written in some papers by Velázquez and collaborators, so there is a way to estimate this integral. Okay, so this is what it happens for kappa equals 0, that you had a very explicit change of variables. Now, what happens when kappa is not from is different from 0? Then basically you have to relate, you have to introduce factors comparing theta and theta minus kappa. But you see that since both of them have the same behavior at infinity, there are just factors running around your integrals that make the formula more complicated, but they don't mess up your asymptotic behavior. So, okay, I think just summarizing that to do non-local ODE is tricky because it's not an ODE that you can plot. But we have used some very classical analysis tools like complex variables or variational arguments, etc., to try to do this ODE theory. Thank you very much.
Thank you, Maria. Are there questions or comments for Maria?
I have a question.
Please, Veronica.
Yes. So can you say something about this curve of the symmetry breaking, apart from it has this different behavior? I don't know, for example, can you say that it is regular, that it approaches the origin, or what can you say about that?
Not much, but we didn't try hard enough.
Okay.
The thing is, that's why I wanted to discuss with you. The thing is that part of your work relies on a specific knowledge of the spectrum of the Schrödinger operator, and we don't have that. So that's the goal. So whenever we can travel, I will invite you to Madrid.
Okay. Thank you.
What is the
other comments or questions?
Yes, I have a question. I can. Many thanks, Maria. Very a wonderful talk. I have appreciated very much this new topic for me. And I want just to ask you, what about this infinite system of ODEs? And if there is in some sense, the possibility of making a hierarchy of trying to keep just the more important ones, if there is something in this direction to make numerics in some sense. You are able to join very in a wonderful way convolution, the meaning of convolution and of a local operator by giving this system of infinite equation. But I want to know if some attempt is possible to try to find out the more interesting equation to solve in order to have an approximation of your solution. Thanks.
Well, I have no idea. So like, I think we use this because we needed to develop this theory for our problem, but we haven't really exploited. So we did you can write a Hamiltonian or you can write a Wronskian, and we use those things, but that is nothing else.
Okay, thanks. Very good work.
Thank you.
Other questions? Okay, if not, let's thank again Maria for her talk. Thank you, Maria.
Thank you to you. Bye-bye.
Okay. Now our next speaker is Andrea Pinamonti. Okay.
Yes. Hi. So can you share my screen now?
Yes. Try to share your screen. So Andrea Pinamonti is from Università di Trento.
Do you see now my screen?
Yes, I can see the screen.
Okay, perfect.
And here we speak about gamma convergence and H convergence for functionals and operators depending on vector fields.
Okay, so first of all, let me thank you, the organizers. It's a great pleasure for me to have this opportunity to speak in this very nice meeting. The plan of this talk is to tell you something about a research project that I have in collaboration with many people here in Trento. And so some of them are listed here. So it's Alberto Maione, Francesco Serracassano, Fares Essebei, and Simone Verzellesi. And the basic idea is to try to see what happens to some notions of variational convergence, like the H convergence, when you move from the Euclidean world to a very degenerate setting. So the plan of the first part of this talk is to tell you what I mean by degenerate setting. And then I will move to the description of the actual result. And if time permits, I will tell you also something about the proof. But okay, so the setting is the following. So from now on, we will work in Rn, and we will fix a family of M vector fields. So x1, xm are vector fields on Rn. And for me, a vector field is just a first order differential operator, like the one in the slide, with locally Lipschitz coefficients. Okay, so xj is just an expression having the form displayed in the slide, where the functions cji are locally Lipschitz functions. And so let me also call x gradient the vector whose elements are the vector fields that I have chosen. So capital X is a vector whose components are x1 to xm. And let me also introduce the so-called coefficient matrix that it will have a very that will play a very important role later on. So the coefficient matrix is just is nothing but the m times n matrix defined as follow. So you put in each row of the metric the coefficient of the corresponding vector field. Okay, so in the first row of your matrix you have just the coefficient of x1, and the second row is the coefficient of the x2, and so on and so forth. So this is basically the setting. So it is very general setting. And indeed, it is too general. In fact, I need to restrict a bit the generality of this presentation, because from now on, I will always assume that the family X satisfies this linear independence condition, which is actually a very mild assumption. And the condition is tells you the following. So you say that the family X, capital X, satisfies the linear independence condition if there exists a set, let's say nx, which is a subset of omega, and with the property that the set x nx is negligible, so with Lebesgue measured 0, and with this additional property. So if you pick any point outside the set nx, the family x1 evaluated at x and xm evaluated at x is a linear independent set of vector in Rn. Okay, so this is a very mild assumption, but we really need it in order to prove our result. And actually, so the first observation, the first actually very trivial observation is the fact that with this condition, the number of vector fields that you can choose is actually less or equal than the dimension of the space for obvious reason. And let me try to give you some relevant examples of vector fields satisfying the Lick condition, so the linear independence condition. So the first one is the trivial one. So when you take as X, the family of vector fields defined in the following way. So X1 is just the derivative along the first direction, and Xn is just the derivative along the last direction in Rn. So what I'm saying is that capital X is nothing but the standard Euclidean gradient in Rn. In this case, this family trivially satisfies the condition with Nx to be the empty set. Okay, so meaning that the theory that I'm going to present really extend the Euclidean theory. The second example is a less trivial one, but it has some relevant geometric consequences, and it is the Grushin family of vector fields. So you are now in R2, and you take x1 and x2 defined and as in the slide. So x1 is just the derivative along the first direction, and x2 is just x1 times the derivative along the second direction. And it is very easy to prove that also this family satisfies the linear independence condition with nx, the set displayed in the slide. So you just have to take the line x1 equal to 0, which is obviously a set of two-dimensional Lebesgue measured 0. Another more important example is the one coming from the geometry of the Heisenberg group. So you are now in R3, and you take two vector fields, x1 and x2. And the expression in coordinates is the one in the slide. And also here it's very easy to prove that this family of vector fields satisfies the condition. And here let me point out the fact that this is the first example where you have a number of vector fields strictly less than the dimension of the space. And a less trivial example is, well, it is less trivial in a sense that I will tell you in a moment, is the following. So you are now in R3, and you consider the family x1 as the derivative along the first direction, and x2 the derivative along the second direction. Okay, and trivially this family satisfies the linear independence condition, and the difference for this example with respect to the previous one is the following. So if you look carefully at the previous example, all of them share a common property. So all of them satisfy the so-called Ormander condition, meaning that you can reconstruct all the directions in the tangent space of your manifold, taking the vector fields that you have and sufficiently big number of commutators. And whereas the last family in the slide does not have does not satisfy the Ormander condition, because no matter of how many commutator you do, you will not be able to reconstruct the missing direction, which is the last one in this case. Okay, so the point is that for this theory, the remainder condition is not a priori assumed; it's not necessary. Okay, so so this is my setting. Okay, so this is the setting where I will work. And now let me tell you something about the notion of functionals depending on vector fields. Okay, so this will be the main character of my presentation. So I will try to explain it carefully. So for me, a functional depending on vector fields is just a map from LP to 0 plus infinity, and and throughout my presentation, P will be always between 1 and infinity. We are not able at the moment to handle the limit cases, and f of u, sorry, and f of u. Oops, what is going on here? Okay, and f of u has this property. When you compute it on a regular function, so say for a moment c1, f of u is actually expressible as an integral. Sorry, I don't know what is going on here. Okay, as an integral function. So it is an integral over omega of a function f, which depends on little x and the family capital X evaluated at u. Okay, and if you take and if you compute the functional u f on a function u which is not in C1, you just get plus infinity. Okay, and in order to have a well-defined object, as in the standard calculus of variation, we need to put some restrictions on the function little f, and the restriction that I will assume throughout this talk are two. So the first one is the fact that f is little f is convex in the gradient variable, and the second one is that you have some growth assumption from above and from below. Okay, so here is see here for this presentation, f is assumed to be less or equal than c1 times the norm of eta to the power p, and the same from below. Okay, and these are very common assumptions in the calculus variations. Okay. Okay, so now let me give you a very easy remark, but it will be crucial for us, which is the following. So when you consider an integral functional depending on vector fields, so an expression as in the slide, so an integral with the standard gradient, where you instead of taking the standard gradient, you just take the family capital X. And when you compute it on regular functions, then what you can do, what you actually immediately realize is that you can rewrite your function as a functional depending on the Euclidean gradient, right? Because you can just consider this the new function little fe depending on xc, which is defined as f, sorry, evaluated at x. And in the gradient variable, what you take is just the coefficient matrix evaluated at x times the variable c, right? So when you compute, if you do this substitution, what you immediately realize is that any integral functional depending on vector fields evaluated on regular functions is actually a standard functional depending on Euclidean gradient. And this is, a trivial observation, but it has some important consequences. Now the question is the following. So are you able to prove the opposite? So meaning that starting from a functional depending on the Euclidean gradient and having fixed a family of vector fields, are you able to rewrite your functional in terms as an integral function that just depending on the family capital X? And this is actually, and the answer to this question is not so trivial, and is actually no in general. Indeed, we characterized, we identified an algebraic property that the function fe has to satisfy in order to to be able to go back in this representation. And the property is the one in the slide. So what we have proved is that the opposite representation holds if and only if the function little fe is evaluated at xc is equal to little fe evaluated at x pi xc. And I'll tell you in a moment what, and I tell you now actually what I mean by pi x. So pi x is nothing but the projection, the orthogonal projection of a point in Rn on the onto actually the vector space generated by the family of vector fields that you have fixed. Okay, so the point is you have fixed a family of vector fields from the very beginning, satisfying the leak condition. You have an integral functional just depending on the Euclidean gradient, and the question that I wanna study is, are we able to represent this function as an integral function depending on the family on the family X? And the answer is yes, if your density, if the function little f satisfy the algebraic property displayed in the slide. And okay, so here I have put an example. So so if you take, even if you take a very easy functional, so for example, take p equal to 2 and consider the functional f from L2 cross omega, sorry, from L2 without cross omega, to 0 plus infinity, which is defined as in the slide, is just the L2 norm and L2 norm squared of the gradient of u, when u is a function in W12. And suppose that you have fixed as the family of vector fields the one coming from the Heisenberg Lie algebra, okay? And it is kind of easy to prove that actually you cannot represent this functional, so f of u, as a functional depending on the vector fields coming from the Lie algebra. And the reason is simple. It's just the verification that the density of the functional capital F does not satisfy the algebraic relation. Okay, so the point is that even if you consider very easy functionals in the calculus of variation, it is not trivial a priori to go back and forth from the representation in terms of the Euclidean derivatives and vector fields derivatives. Okay, so I will skip the details, but the point is that the one that I have told you. Okay. Okay, so let me try to give you some examples of functions, of integral functions that we are able to handle with this theory, and let me also try to give you an important motivation from the calculus of variation to study these functions from with our point of view. So, for example, if you take as capital X the Grushin family, and if you take as a density f x eta just the norm of theta to the square, the function f of u, you can write the function f of u as the one in the slide. And similarly, if you take as the family X, the one coming from the Heisenberg Lie algebra, what you get is the function displayed in the slide. And both these functions have a property which is very bad from the point of view of standard calculus of variation, which is the fact that they are not coercive with respect to the Euclidean norm. And meaning that you cannot, I mean, you might have serious problem to, apply the standard theory of the calculus of variations to these two variational functions. Okay, so but despite this problem, we are able to handle these two functions using our approach, our theory. Okay, well, our approach. Okay, so in order to now give you the statement and tell you precisely what we have proved and what I mean by gamma convergence in this setting, I need to give you, I need to introduce or remind you a bit of, I mean, the notion of Sobolev spaces driven by vector fields, or defined upon the definition of, upon the notion of vector fields. And this notion is actually super classical. It goes back to Folland and Stein. And the definition is the following. So it is the one that you can imagine. So if you pick P between 1 and plus infinity, you define W1px or of omega as the set of functions in LP having distributional derivatives along the vector fields in LP. Okay, so what you can prove is the fact that you can endow this space with a norm, and with this norm the space become a Banach space, as in the Euclidean case. And you can also prove that there is a relation between the standard Sobolev space, so the one that you get taking as x just Euclidean gradient, and the Sobolev space W1px. And the relation is the one in the slide. So precisely W1p omega is contained, is actually strictly contained in W1px, okay, for any x. And the last definition that I need is the notion of W1px0, which is nothing but the closure of the set of regular functions with compact support in the Sobolev norm. So precisely as in the Euclidean case. Okay, so this all these definitions are super classical, and but I mean they are very, very helpful in our case. Okay, so before telling you what we have proved, let me just briefly remind you the notion of gamma convergence and the reason why it is so important in the calculus of variations. So gamma convergence is a notion of variational convergence. So it is a notion of convergence at the level of variational functionals. It has been introduced in the 70s by Ennio De Giorgi, and among the precursors of the theory, one should also mention the Moscow convergence, which is another very important variational convergence, and the G convergence introduced by Spagnolo, which is actually a notion of convergence for differential operators. And nowadays, as I said, the gamma convergence is, I mean, a fundamental tool in the calculus of variation. It has very, very important consequences. And the definition is very briefly the following. So you can define it in a metric space. So XD is a metric space, and you define and you take a sequence of functions. Capital Fn from let's say x to the real line, and you assume that they are lower semi-continuous. Okay, so you can define two quantities, two new functions. So the first one is the so-called gamma lim sup of the sequence Fn, which is defined as the infimum of all the lim sup of what? Of Fn evaluated on every sequence Xn with the property that the sequence Xn converges to X. Okay, so you have fixed X and you can define the gamma lim sup as in the slide. And you can also define in the same way the gamma lim inf. Okay, so it is, I mean, clear from the definition that you have a relation between these two guys, and the obvious relation is the fact that the gamma lim inf is always less or equal than the gamma lim sup. But you say, I mean, the definition of gamma convergence asks for the opposite inequality. So basically you say that the sequence Fn gamma converges if you also have the opposite inequality. So basically if the gamma lim inf coincides with the gamma lim sup. Okay, well, there is also a more effective definition of the gamma convergence, but I prefer to stick to this one. And let me tell you, I mean, probably the result, I mean, the most important result in this theory, which is this one. It is a very classical result, but, I mean, it tells you basically the following thing, that if you have a family of functionals gamma converging to something, under a reasonable assumption on your sequence, what you can get is, you can get also information at the level of the convergence of the minimizers of the sequence Fn. So basically, gamma convergence is a tool also to get information at the level of minimizers of the function. And this is at least from my point of view, one of the main motivation to study them and to use the gamma convergence in the calculus of variation. So more precisely, suppose that the sequence Fn gamma converges to the functional f, and take a sequence of points verifying the inequality in the slide. Then the first thing that one can prove is that then any limit point of the sequence is actually a minimizer of f. But in addition, if you assume the so-called equicursivity of the sequence, meaning that the following, so if you compute the infimum of the sequence Fn over x, then this infimum is actually equal to the infimum over a compact set K, which is independent on n, and this is actually the crucial part. So equicursivity precisely means that there exists a compact set verifying this equality. Then actually you can prove you can prove more, in the sense that you can prove that also the minimum value of Fn converges to the minimum value of the capital F. Okay, so this means that using gamma convergence, you can study the minimizers also of the limiting function. And this is, as I said, one of the most important results in the theory. Okay, so let me try to give you the problem and tell you the problem I have investigated with Francesco and Alberto. So the problem is the following. So you have a family of vector fields on Rn. So you have X, which is a family of M vector fields on Rn. And you consider and you take a sequence of functions fh in the set IMP. And let me just quickly remind you what I mean by IMP. This is nothing but the set of functions which are convex in the second entry and which satisfies growth assumption from above or from below. Okay, so now once you have this this sequence, what you can do is to look at the associated variational functional. So you consider capital F H as the variational functional defined upon the sequence little fh, and here, sorry, oops. And here U is supposed to be in W1px. So okay, so the function is defined as in the slide. So when U is in W1px, you get this expression, and if you take a function outside W1px, you just put the function to be equal to infinity. So the question we are interested in is the following. So basically, we investigated the gamma compactness result for integral functionals depending on vector field, meaning that the question that we looked at was the following. So are there functions, are there a function f in the set IMP and the limiting function, in a sense, capital F from LP to 0 plus infinity, with the property that your starting sequence FH gamma converges to F up to, let's say, subsequence. And more importantly, are you able to represent the gamma limit as an integral functional? So this is basically the problem we are interested in. So you have a family of integral vector fields, and we wanted to see if the gamma compactness result, which is a very well-known tool in the Euclidean case, is still true in this new setting. And okay, so it turns out that the answer is positive, but the proof is kind of involved, and I will try just to give you some very quick ideas of the proof. But before giving the proof, let me give you a warm-up result, in a sense. So what happens if you take as the sequence fh just a sequence of functions which are all equal. So fh is equal to, let's say, f for any h. So it is known from the standard theory of gamma convergence that in this case the gamma limit exists, and is actually the relaxed functional of f, where the relaxed functional for me is defined in the following way. So it is over bar f evaluated at u is the infimum of all the liminf of f evaluated on every sequence uh, with the property that converges to u in LP. Okay, so this is a very well-known object in the calculus operations. And so the first result in this setting goes back to Franchi, Serappioni, and Saracassano, and indeed they proved that so you have the gamma limit. The gamma limit is the relaxed function, and this is just the standard theory, but you can also reconstruct the gamma limit as an integral function. So meaning that the problem we are interested in has positive answer, at least in this very specific case. Okay, so at least when you take everything to be constant, you have a positive answer to our problem. So our goal was to try to generalize this result to the full generality. And indeed, what I proved in collaboration with Alberto Maione, who is now actually a postdoc in Freiburg, and Francesco Saracassano, is the following result. So under the assumption that I told you before, so you have a family of vector fields satisfying the Lick condition, and you have a family of functions, little f, and you consider the associated variational functionals, then up to subsequence, you can prove that there is a gamma limit with respect to the LP topology. And more importantly, that as before, you can reconstruct the gamma limit as an integral functional. Okay, so this basically tells you that the gamma compactness result proved by Buttazzo et Almaso many years ago, actually, holds also in this very, let's say, degenerate context. And okay, so let me just give you two ideas of the proof. I mean, we started trying to generalize directly the proof of Buttazzo and Dalmaso to this setting, but we failed. And the reason why we failed is basically the following fact. One of the crucial points in the proof of Buttazzo and Dalmaso is the possibility to approximate any Sobolev map with, let's say, piecewise affine functions. And but this result is not true in our case. So we after many months, we actually constructed some examples of functional which are not for which you cannot have any approximation by affine function, where here affine has to be intended in a precise sense. So the idea, so we found a way to overcome this problem, and the way was the following. So first of all, we did the following. So you consider your family FH evaluated on regular function, and when here regular is really regular in the Euclidean sense. So here W11 lock is the standard Sobolev space. And remember that W1P is always contained in W1PX. And so for the motivation that I told you before, once you have a regular function, you can always represent an integral function as functional with Euclidean derivative. So now the point is to prove that you can apply the standard gamma compactness theorem due to De Giorgi, to Buttazzi and Dalmaso. And this is a non-trivial point, but you can do it. And once you apply the result by Buttazzi and Dalmaso, what you get in the limit is a functional which you can write as a functional depending on the Euclidean gradient, and this is crucial. Okay, but because you are just using the Euclidean result. So now the problem is, are you able to go back? So meaning that you would like to express the gamma limit that you got in terms of an integral function depending on the family capital X. And this is pretty much connected to the problem that I was mentioning at the very beginning of this talk. And indeed, the second main point of the proof was to prove that actually the gamma limit that you get using the Buttazzi and Dalmaso result can be expressed in terms of the family of vector fields that we have chosen. And this is non-trivial in the sense that we have, we proved an integral representation result for functionals in terms of vector fields. And as I said, the proof is kind of complicated. But the basic idea, I just wanted to put your attention on this fact, that we are not able to follow or to directly generalize the Euclidean proof, but we needed to find a different path. Okay, and okay, so let me try to give you two important consequences of this, or two nice at least consequences of this result, which are also true in the Euclidean case. So the first consequence is the fact that if you consider the subclass of functions of density, let's say, and which depends only on the gradient. So this is a family closed under gamma convergence. So meaning the following. So if you start from a sequence of functions which depends only on the x gradient, you can apply our theorem, and in the limit, the gamma limit a priori is just an integral function depending on x and on the gradient. What you can actually prove is the fact that you can drop the dependence on the space variable. So if you start from a sequence of functions just depending on the gradient, the gamma limit is a function just depending on the gradient. And the second result is actually a similar result. So if you start from a sequence of functions which are quadratic forms. So what I mean is the density is actually a quadratic form. You can still apply our result, and in the limit you still get a quadratic form. Okay, so this means these are closed classes in the gamma convergence. Okay, and let me tell you very briefly that I'm now working with Fares Essebei, who is a PhD student in Trento, and Simone Verzellesi, who is a master student in Trento, in the generalization of all these results to the complete case, with complete I mean that I want to also put the dependence on the function. So in a paper that we have just submitted, we proved an integral representation result in terms of function depending on x, u, and the gradient. Okay, and the second step is now to investigate what happens to the gamma convergence and so on and so forth. Okay, so this is basically how much time do we have still?
4 minutes.
How many?
4.
4?
Yes.
Okay, so let me just tell you very briefly something about the H compactness problem, which is the second part of the paper with in collaboration with Alberto and Francesco. So in the second part of the paper, we investigated the so-called H compactness problem. So H compactness is a notion of convergence at the level of differential operators. And here the differential operator that we used or we investigated is the one in the slide. So they are open. So this is this L here. So it is the divergence with respect to the family X, and I tell you in a moment what I mean by this, of what? Of a matrix A, which satisfies certain assumptions, times the X gradient. Okay, so here the divergence with respect to the family X is what you might expect. So you just take the sum of the derivative along the element of the family capital X. So meaning that if you just take as X the Euclidean gradient, what you get is just the usual differential operator in divergence form. And since okay, so let me just tell you in 2 words what we proved. So in order to investigate the H convergence, we needed to assume some extra assumption on the space. So we needed to put 3 main assumptions. So the fact that the family capital X generates a distance, the fact that the distance is doubling with, the Lebesgue measure is doubling with respect to the balls defined with respect to this distance, and this technical assumption, which is H3, which you can just consider as assuming the Poincare inequality. This is not really true, but I mean, first approximation to this, the Poincare inequality. And so let me just mention that all these 3 assumptions are satisfied in many cases. So for example, when you take any Carnot group or any vector fields, any family of vector fields satisfying the Ormander condition, all these 3 assumptions are satisfied. And the reason why we needed to assume these 3 assumptions is the fact that we wanted to prove, we wanted to have at our disposal this theorem. In particular, what we wanted to use is the fact that W1px0 is compactly embedded in LP. So this is super standard in the Euclidean case. It is not so standard in when you take vector fields, and this is actually something that you have to prove by hand. So this is a result actually due to Nicola Garofalo and Nieu, and there is the same result in a paper by Franchi, Serappioni, and Sarcassano. And okay, so let me just conclude giving you the result that we proved in this setting. So this is an H compactness result, so meaning that we considered a sequence of operators, of differential operators, LH, and each of these LH is a differential operator as the one that I told you before in terms of a specific metrics. Okay, so now you have a sequence of differential operator. You can look at the solution of this differential operator in H1x0 with suitable datum. So okay, so I'm going too fast, but you have to look at the solution of the problem in the slide. And let me call the solution, the family of the solution, UH. And basically what we proved is actually that this family, there exists a limiting problem with the property that the sequence of solutions strongly converges in L2 to the solution of the same problem in the slide, and also you have the weak convergence of the momenta of the solution. This is what it is known in the literature as H convergence. Okay, so sorry, I went too fast in this part, but this is actually okay. So I will skip completely the proof, but let me just tell you. Let me just stress one point. So if you look at the Euclidean proof, this is mainly based on the notion of Carl. So you have to use in a very strong way the Div-Carl lemma, and this is forbidden in our case because, as far as I know, there is no reasonable notion of Carl in this very degenerate setting. So there is a notion of Carl for Carnot groups, which is actually a subclass of spaces verifying all our assumptions, but as far as I know, there is no general notion, and therefore we needed to find a way to overcome also in this case this problem. And the main idea went from this paper, this actually very nice paper from by Ansini, Zeppieri, and Gianni Dalmaso, where they proved that actually you can get the H convergence for linear operators just using tools coming from the gamma convergence. Okay, so I mean, we really investigated this paper, and we found a way to overcome the problem also in our case. So sorry for the overtime, and I conclude here.
Thank you, Andrea. You are in perfect time, don't worry.
Huh?
You are in perfect time.
Okay, perfect, thank you.
Are there comments or questions for Andrea?
Ciao Daniele, ti vedo qua.
Ciao Andrea, grazie del bel seminario.
Okay, no questions? Okay, if not, let's thank again Andrea for his talk.
Thank you to you.
Andrea. And I also want to thank both the speaker of this afternoon session, Maria De Nogueras and Andrea Pinamonti.
Okay.
Then the last speaker of this meeting is Claudio Nora Albes. It's a great pleasure for us to have Claudio Nora as a speaker in this meeting for several reasons. But I just want to thank again Claudio Nora, and please.
Okay, thank you very much. I would like to thank my friends Giovanni and Rafaela by invitation. I am very happy to be here in this very nice opportunity to see more one time my Italian friends. Thank you so much for the invitation. Today, I will talk to you some recent results involve one Laplacian operator in whole Rn. In the last 4 years, I am studying variational problems where the energy functional is defined on non-reflexive Banach space. Okay, today I will show for you one part of this project. And I will intend to show for you 3 papers. Of course, I will avoid technology. Okay, my intention is to show for you the result, because if you like or intend to read the paper, you can find the details of the estimates. The first paper is one paper in collaboration with my friend Marcos Pimenta, and the second paper is one paper that I wrote alone. Is one heuristic type results for one Laplacian operator. And the first paper is one paper involving existence and concentration of solution. And the paper 3 is one paper involving existence of multiple solutions for one Laplacian operator. Okay, let's go. In the paper 1, I studied with my friend Marcos Pimenta the existence and concentration of solution for problem 1. Here you can see in the left side of the equation appear the one Laplacian operator. Okay, and our intention here is to use variational methods. Okay, have this in mind. Of course, we need to assume very good assumption of the function f. For example, we assume the conditions f1, f2, and f3. This condition help us to consider one energy functional associated with the problem 1. But we need to consider more 2 conditions. The condition F4 is well-known Ambrosette-Rabbit-Novit condition that help us to prove the boundedness of the PS sequence. And the condition F5 is very important when we need to characterize characterize the some properties involving the mountain pass level. About the potential V, okay, we take the same conditions of Rabinovitz in the famous paper by Professor Rabinovitz. Okay, we have a one potential V in L infinity and satisfying this condition. Okay, the motivation to consider the problem one, okay, comes from of one rich literature involving the problem as epsilon. Because in the literature, okay, we find very nice papers where the authors study the existence and concentration and multiplicity of solution for this problem. And here I wrote some of reference. Unfortunately, it is impossible to write one full bibliography, and here I cite some of them. In this paper, okay, that I show for you in this moment, the authors establish the existence and concentration of positive solutions for problem S. It's important to see that the operator here is the classical Laplacian operator. In this paper, in general, the authors use variational methods to establish the existence of weak solution for the problem. For that problem involving the Laplacian operator, we have a very nice energy functional. Here, I show for you the functional I, which is well defined in this Hilbert space, H epsilon, and do it with this norm. In this case, the energy functional is one C1 functional. And in this case, we have the space H epsilon is reflexive because it's one Hilbert space. In general, okay, the behavior of the potential V affect the number and the behavior of the solutions when epsilon is small enough. For example, when the V has one global minimum or local minimum, global minimum, for example, in the case of Rabinovitz, local minimum in the paper by Urbino. It is possible to prove the existence of one family of solution when epsilon is small enough, such that the family of solution has the following property. The maximum points of the solution concentrated around the minimum point of the potential V when epsilon is small enough. For this class of problem, it's very, very important to have one very nice regularity theory. And of course, the fact that the Laplacian is one linear operator help in a lot of estimate. When we try to repeat the same approach for one Laplacian operator, we find a lot of difficulty because, for example, in your case, the natural candidate to be the energy functional is the functional I given by in the sentence 2, where in the first integral is the total variation of one measure. Okay, so we lost the differentiability of this functional. And the natural space to work in this case is the BV in Rn. Okay, BV space in Rn, and I recall for you the definition of BV in the sentence 3. In this situation, okay, it's well known that BV space is one Banach space, and do it with this norm in blue. But the point of view of the continuing embedding the BV space is good to work because we have a very nice continuous embedding involving BV because BV is continuous embedding all LR for R between 1 and 1 star. But we find two big problems in order to apply variational method. The first one, the BV space is not reflexive. Have this in mind, it is impossible to use weak topology. Moreover, we have the energy functional is not C1. In your case, it's only local Lipschitz, okay? So when you recall all the technique using in the paper of Rabinovich and the paper of Delpini, Fermat, etc., it's very, very hard to repeat the estimate. It is necessary to introduce new ideas, new estimate in order to prove one quite similar result involving one Laplacian operator. Once that we are trying to apply variational methods for one functional that is only local Lipschitz, okay, we are leading to use convex analysis. And here we recall that one critical point of the functional I, this functional I here, is one point such that 0 belongs to the subdifferential of the functional I at the point V. When we use the properties of the subdifferential, it is possible to prove that this definition is equivalent to prove this inequality 4. Okay, this inequality 4 is the inequality that characterizes the critical points of the energy functional y, I. But one very important point is to understand what is the relation involving the critical point in the sense 4, because in the sense 4 is close to when you are working with variational inequality, okay? And in this case, it is possible to prove of one precisely way that one function V satisfies this inequality. It is possible to find one field Z and one scalar function Z2 star such that this function satisfies all these conditions in red. This condition is in red are precisely the definition of solution when we are working with one Laplacian operator. But here I would like to tell for you more some difficulty involving the BV space. For example, when we work with H1 of Rn, we know that the space of C0 infinity is dense in H1 of Rn. But in BV, it's not true, okay? So it is necessary to introduce one new type of convergence. For this type of problem, the new type of convergence that works very, very well in a lot of paper is the intermediate convergence. Here, I recall for you the definition of the intermediate convergence. We say that one sequence converges in the intermediate convergence sense when the sequence converges to U in L1 and the total variation involving the sequence UN and U satisfy this limit in the end line. Okay. Here, I show for you our result, the main result in the paper one. In fact, we were able to prove essentially the same result. We proved that there is one ground state solution when epsilon is small enough, and we proved that when you fix one sequence epsilon n goes to 0, this sequence concentrate around one minimal point of the potential V. And these properties involving the integral of the nonlinearity F hold. This inequality involving the nonlinearity F establish, in some sense, the concentration around the point x0. Okay? Now, I will talk to you very fast about the idea involving the proof of the theorem 1. Of course, we will use the variational methods. We will work with the mountain pass level. And we prove that the mountain pass level, okay, can be characterized by using the infim of the functional I on this set. Here I call Nehari set, because when we work with Laplacian operator and we have a very nice regularity and properties on the nonlinearity, it is possible to prove that this set and epsilon is in fact one manifold, but in your case, no. You can see that in the definition of this set appear I prime. I prime here, we need to understand how the directional derivative of the functional I at the point u in the direction of u, because this functional is not C1, but when you fix one point and you compute the directional derivative in the same direction of u, you can prove that this limit exists. Have this in mind. This Nehari set is well defined, and you can prove the above characterization involving the mountain pass level. And now, associate with the mountain pass level, it is possible to prove that there is one PS sequence by using the seminal paper due Professor Zukin. And in this case, the PS sequence is one sequence that satisfies the conditions 5 and 6. See that in 6 we have again one inequality. For this type of problem, the big challenge is the fact that in any moment you need to work with inequality, while when we work with Laplacian, we work with equality in some estimate involving the energy functional. Here, okay, it is possible to prove, it's not difficult, that the PS sequence is bounded. And after some computations by using the intermediate convergence, it is possible to prove that there is one function V epsilon in VV space, such that the PS sequence is strongly convergent in LQ log, and this limit 7 hold. I would like to talk a little bit about the limit 7. The limit 7 in general is very important when we are working with variational inequality, because different of the case when you are working with Laplacian, okay, the limit 7 is not necessary to prove that the weak limit is one critical point, because you can use it of the groove of the nonlinearity. It's not difficult to prove in general that the weak limit is one solution of the problem. The problem is to prove that the weak limit is not trivial. This is another problem, okay? But here, we need to prove this. For example, we need to prove this limit if you are working with Laplacian in whole Rn, and you need to prove the PS condition. This limit is crucial. But to prove that the weak limit is one critical point, in general for Laplacian, this limit it's not crucial. But in your case, this limit is essential, because we need to take the limit in this inequality 6. And in order to do this, you can see that it's impossible to use Fatou lemmas to get this estimate here for the function v epsilon. It is necessary to have in your hands the limit 7. So why can prove this? The first step is to prove the limit 8, because if you have the limit 8, of course, it's easy to prove that limit 7 holds, because you can use the group of the nonlinear f together the Lebesgue's theorem. But the big challenge is to prove the limit 8. How we can prove this? We can prove this using the concentration of compactness principle. We set this sequence, whole n, and we studied the 3 possibilities: vanishing, dichotomy, and compactness. And we were able to prove in your paper that vanishing and dichotomy does not hold. So in your case, we have compactness in your hand. If you have compactness in your hand, we have a very, very good information about the sequence, because in this case, we have one strongly convergence in L1 of whole Rn. Now, when we combine this convergence in L1 with the interpolations properties of the Lebesgue space, we get this limit of the sequence Vn to V epsilon and LQ of Rn for Q between 1 and 1 star. Okay, this is a very, very, very important point in order to take the limit in the inequality 6 to prove this inequality 4 to conclude that the function V epsilon is one solution. In your case, we prove that this solution achieves the mountain pass level, so this solution is non-trivial. This is the hard part of the paper, because the second part of the paper that involves the concentration phenomenon is quite similar to Laplacian case, because you fix the family of the solution. It is possible to prove by using the Berestik-Lyon, the Lyon's type theorem, that you find one family of points y epsilon that satisfy the inequality 9. And when you fix one sequence epsilon n goes to 0, it is possible to prove that the sequence epsilon n y n converge to one point y star, where this point y star achieve the infimum of the potential V in whole Rn. Using the sequence yn, we can define one new sequence Vn tilde by using one translation. And we work a lot with the new sequence, and using again the concentration of compactness principle, we prove that the limit 10 holds. If the limit 10 holds, okay, it's easy to prove that these inequalities involving the nonlinearity here, it's hold. Okay, this is the basic idea. Here I show for you some interesting papers involving one Laplacian operator. Here we have two papers of my friends Giovanni and Marcos Pimenta. The second paper. In the second paper, okay, we study along this type of problem, and my intention in the second paper was to prove one Berestik-Lyon's type result involving the one Laplacian operator. But in this case, I used one approach totally different of the paper one, because in this case, I introduced the approximation technique for problems involving one Laplacian operator in whole Rn. This technique is well known when the domain is bounded. For unbounded domain, this is the first paper that uses this technique. This technique, essentially, the basic idea is the following. we consider one class of P-Laplacian problem associated with problem 11. We take a lot of limit. We pray for God that the estimate is good. And after a lot of estimate, we take the limit when P goes to 1, and we prove that the sequence of solutions for P-Laplacian problem converge for one Laplacian problem. This is the idea, okay? Of course, the technique behind of this, it's difficult because you need to have one precisely control on the constants that appear in a lot of estimates. And the motivation, of course, is the papers do a Berestik-Lyons and Berestik-Galois-Cavian, where in this paper, the authors studied the existence of solution for this elliptic equation in red, okay? In the dimension n bigger than or equal to 3, Berestik-Lyons established the existence of non-trivial solution for the problem 12 by supposing on the nonlinearity only these three conditions in red, okay? We see that there is no Ambroset-Rabinovitz condition involving in this case, okay? The condition G2 essentially say that the nonlinearity has one subcritical growth at infinity. For dimension 2, Berestik, Galois, Cavian studied the case where the nonlinearity has one subcritical exponential growth, okay? The idea is to use variational technique, more precise minimization technique. Here I see for you some papers involving the Berestik-Lyons type problem. In the paper 1, I worked with Ronaldo Duarte and Marco Aurelio Souto, and we proved that behind of the approach used by Berestik-Lyons, there is one abstract framework. In the paper 1, we prove one abstract framework such that the Berestik-Lyons can be proved as one particular case. And we use this abstract theorem to establish more general situations involving the Berestik-Lyons type problem. For example, we prove one version of Berestik-Lyons type problem when the nonlinearity G is discontinuous. In the paper 2, I worked with my friend Marcelo Montenegro and Marco Aurelio Souto, and we prove the one version of Berestik-Lyons when the nonlinearity G has one critical growth for n bigger than or equal to 3, and for dimension 2, the critical exponential growth, okay? This is another paper that studied this type of problem. In the second paper, we studied two cases like Berestik-Lyons, the positive mass and the zero mass case. In the positive mass, this is the model, okay? The problem 13 is the model of the positive case. And here we assume essentially the same condition of Berestik-Lyons, okay? Essentially the same condition of Berestik-Lyons. And we were able to prove the existence of solution for the problem in the sense here, okay? For zero mass case, the problem is a little bit different because in the left side of the equation, you can see that does not appear the term U over norm of U, okay? Because in the positive mass appear this term here, but for zero mass case does not appear. If you study or wrote some papers involving, for example, the Laplacian operator, thinking about this problem for T, and replace one Laplacian for Laplacian operator. For this type of problem, the natural space is D12 of Rn. Okay, here it was necessary to introduce one new space. I call this new space BV0 of Rn. BV0 of Rn works in your case like D12 of Rn for Laplacian operator. And for zero mass case, we assume the three conditions, F4, 5, and F6, essentially like Bernoulli-Steinius. And again, we prove the existence of non-trivial solution. The reader is invited to see that in the proof of theorem 2 and 3, we cannot repeat directly the approaches using the paper mentioned above, because in your case, the energy functional associated with problems 12 and 13 are not C1. In order to be more clear, we will discuss a little bit about the proof of theorem 2. Here, we use one approximation technique that consists in work with a class of P Laplacian problem associated with a problem 12. And after we take the limit when P goes to 1. To make our approach work, some properties of the radiality symmetric functions are crucial to establish some strongly convergence in LT. The reader will observe that one must be careful with this procedure because this technique involves a lot of estimating with the parameter P when P goes to 1. Okay, this is I put in red because this is the main point. Okay, when I was writing the paper, I was very careful in the estimating involving step by step with the constant that depends on the parameter P. The approximate technique in P Laplacian is well known for one Laplacian problem in bounded domain. Here I cite the paper that used this type of technique, but this type of technique for one Laplacian operating for Rn was introduced in this paper, and I studied the existence of multiple solutions. This paper, you try to talk to you after this paper. Okay, here I mentioned more one time some references involving the Laplacian operator. Here more. Here you can see that I wrote in green this article involving Ortiz Chata and Marcos Pimenta. In this paper, the authors prove one version of one Laplacian operator type Bernoulli-Steinius, but the nonlinearity satisfies strong assumptions. Okay, the technique used by Ortiz Chata and Marcos Pimenta is totally different than the technique that I used in this paper. The idea is the following. We fix one P Laplacian problem associated with one Laplacian problem that you wish to solve. In this case, associated with this class of P Laplacian problem, we have one very nice energy functional, which is C1, that satisfies the mountain pass geometry, and you can prove by using the properties of the radial symmetric function that this functional has one critical point of the mountain pass type. Okay. When you have all this information in your hand, you have one sequence of critical points associated with the P Laplacian problem. Now, begin our challenge. We need to make some estimating and control all the estimating involving the parameter P. In your case, it is possible to prove that the norm involving the space W, 1Pn of Rn is bounded. And after a lot of computations, we prove that there is one function in BV hard of Rn, such that this sequence of critical points associated with P-Laplacian problem satisfy all this information that I mentioned for you in this slide. This inequality involving the total variation, the inequality involving the L1 norm, the strong convergence involving LT, etc., etc. And you can prove that this function U is non-trivial. And using the properties of radial functions, we prove this convergence involves the nonlinearity F. Here, it's not necessary to use the concentration compacts lemma like in the paper 1, because here we have a very nice information about our function, because our function lives in the BV hard space. But in order to conclude that our function U obtained in all this information here is in fact one solution of our problem, it is crucial to prove this claim that I am showing for you in this moment. This is one technical part. We need to establish all this convergence, and with all this convergence, we can conclude that the function U obtained in this estimate is in fact one solution for our problem. Okay, and here we take the definition of critical point for P Laplacian, we take the limit, and we conclude the existence of non-trivial solution for Berestik type problem for positive mass. For zero mass case, we need to introduce the new space. The new space is a BV0 of Rn. The BV0, I said to you again, works like D12 of Rn. And we define BV0 like this. Okay. And one natural candidate to be one norm on BV0 is the function blue. In order to prove this, it is necessary to show that there is one version of the intermediate convergence in this new space. In the lemma 4, we prove this. We prove that in the BV0 space, in fact, we have one intermediate convergence. Have this information in your hand. We prove that this function is in fact one norm, and BV0 with this norm is one space, and we have this continuous embedded, like D12 of Rn. Okay? Again, the idea, we consider P-Laplacian problem. We have very nice energy functional. We have very nice geometry. Using the properties of the radial symmetric functions, we establish the existence of one solution at the Montemperse level. We fix one sequence of critical points associated with P-Laplacian. Again, pray for God to the estimate is correct. We take a lot of estimate, okay, and we prove again, like the positive mass, that there is one function in this new space such that all this information holds. All this information holds. It's nice because, again, we prove one new claim involving the BV0 space of Rn. Okay? In order to conclude my talk, I would like to mention for you the paper 3. In the paper 3, we established the existence of multiple solutions by looking for the geometry of the potential V. In this paper, we proved that the geometry of the potential V affects the number of solutions of the problem 15. In the sense that, for example, if the V has 10 global minimal points, the problem has at least 10 solutions. If the potential V has 20 global minimal points, then for epsilon small enough, the problem has at least 20 solutions. Okay, and here we use again the approximation by P-Laplacian problem. Okay, this strategy is the same, but the approach to prove that solutions are different has a trick. Okay, I will mention for you. Here we have the traditional hypothesis on the nonlinearity. Okay, here we have the conditions on the potential V. I ask your pay attention to condition V3. The condition V3 is essentially the number of global minimum points of the potential V. And the theorem 7, we establish the existence of multiple solutions for the problem, in the sense that if V has at least, if V has L global minimum point, the problem has at least L solution. The idea is the following. Okay, but one moment. The motivation, of course, to consider this type of problem. The motivation to consider this type of problem comes from one seminal paper due Carlo and Dozer, and the author studied the existence of multiple solutions for problem P1. And in this paper, the authors prove that the behavior of the function h in the right side of the equation affect the number of solutions for this equation, in the sense that here, the number of the global maximal point of 8, then the maximum of 8 affect the number of solutions. Okay. Associate with this problem P1, we have another paper that I mentioned here for you. Okay, but what is the idea here? Again, we consider one P-Laplacian problem associated with the problem 15, and we prove that for P-Laplacian problem, when P is close to 1, you have at least L solution. But what is the big challenge here? When you take the limit, when P goes to 1, possible 2 solutions could go to the same point. We need to avoid this situation. How we need to avoid this situation? In this case, we studied the barycenter of the solutions. In this situation, we prove that when you take the limit when P goes to 1, one solution has one barycenter close to the point A1. For the second solution, when you take the limit when P goes to 1, you prove that the second solution, the barycenter, is close to point A2. Again, you repeat this argument, and of course, you have one geometric tool to prove that the solutions that you obtained are in fact different. Okay. Here is again one very, very important tool in your argument is the concentration compactness principle. It's crucial in order to obtain a very nice control of the barycenter of the solutions. Okay, I finish here. Thank you very much for your attention. Okay, sorry if I talk very fast, but I would like to talk about this paper with you.
Thank you very much, Claudio, for your nice talking, detailed talk. Are there questions, remarks?
Yes, if it is possible.
Please.
Okay.
Hi, Claudio.
Hi, Vicente. How are you?
Is it for concerning the first result, the first paper? We assume a global Rabinowitz condition, the potential.
Yes, almost.
Yeah, but is it possible to extend the result for the Pino-Fellmer potential?
Yes, yes. There is one paper due to Chinese guy. Okay. the one theorem involving this class of problem, okay, when we assume one local condition type Delpini-Feldman. Two Chinese guys proved this result.
Okay, and second question, but we find
that. But I would like to mention that in this paper of the Chinese guy is very interesting because they used one version of the Chundiger-Moser iteration for one Laplacian.
Ah, okay.
Okay, this is crucial for Laplacian, right?
You obtain L infinity estimate for the...
Yes, yes, yes.
But you find positive solutions in your paper because I don't understand if it is possible to find the nodal solutions. For the
yeah, okay, but here I was not able to prove the existence of a positive solution. Okay, I'm how can I say, because in general we consider that the nonlinearity f is 0 when t is negative. Yeah. Okay, and after we use the function test u minus in order to conclude. Okay, probably okay, it's possible to do this because right now we have one or two papers involving nodal solutions. Probably one technique used in some of that paper can help to prove this. But here we not focus in this direction because this paper is 2017. Okay? And the existence of nodal solution is more recently.
Okay, thank you.
Okay, thank you. Thank you very much for your questions.
Yes, Claudiano, about your remarks on the Moser iteration scheme that you also found in this paper that you cite. If for instance, you consider F critical or supercritical, for instance, maybe it is possible to use this Moser iteration technique with some idea that you explain now in order to treat the critical and supercritical case?
For critical case, okay. For critical case involving bounding domain, there are two articles, okay. It's possible to work with one star power, one star, okay. The critical, it's possible. There is no problem. Here, it's possible to work again by using in the paper 2E3, okay, by using the approximation, okay, because again here we have a loss of compactness when we work with one star. Here the unique difference, because we don't know what's the best constant of the embedding, okay, but you can prove if you put some parameter in the right side of the equation, you can control the loss of compactness. It is possible to work, okay.
And about
for example, using some strip, okay,
yes,
in your paper, it is possible. My feeling is you can propose one P Laplacian problem, and you prove the existence of a solution on the street. And after you take the limit when the P goes to 1, okay, and it's possible because when you consider P Laplacian problem, you obtain again all very nice information in the Sobolev space.
Yes,
this is the trick to prove that, for example, Strauss-Lyon's theorem holds for BV space. Okay, it's the truth.
Thank you.
Okay, thank you for your remark.
Other remarks, questions?
Giovanni, there is a question in the chat by Kyo, who says, what about the case u equals
yes.
1 star?
Yes, exactly. My question is exactly this.
Okay,
Okay.
so
Yes, can I ask you one question?
Please.
yes.
In the proof of the theorem in paper 1, how can you know C epsilon is verified? C epsilon in the proof of paper 1.
In the paper 1, here
Yes.
we have epsilon.
No, CF, you define C epsilon, based on the Nehari manifold. Could you show me?
Okay.
Because I'm not sure
here.
nullity or not.
The mountain pass level?
Yes.
Okay.
Could you show me? Yeah. And epsilon, how do you know it's non-empty?
This manifold is not empty, okay? Because in this case, it is possible to prove by using properties of Misioud that when you work with the properties of total variation, when you fix one point and you take the limit, when when t goes to 0, the function of y, u plus t, u minus iu over t, it is possible to compute and prove that this direction derivative there exists. In fact, there is more direction that this derivative exists. For example, if you fix one direction, that the direction is vanishing when the point that you are computation, that directive vanish. Okay.
Yes.
And okay, this is a very, very important. There is very nice paper due Professor Giovanni Figueiredo and Marcos Pimenta, where they study the properties involving the Nehari set, and there they prove this characterization involving the mountain pass level.
Yeah, I see. Thank you.
Okay, nice. Thank you for your question.
More comments? If not, many thanks again to Claudio Nor for
thank you.
this talk. Thank you.
Thank you. Thank you.